In 1223, a Mongol army marched across a Siberian winter where steel blades shattered like glass. Weeks later, that same force operated in a desert kiln, hitting 120 degrees Fahrenheit. A standard medieval army would have collapsed in either environment. They required massive, slow-moving supply trains just to survive. If you severed that line, the army died. Yet the Mongols carried no grain wagons and maintained no fixed depots. They moved across tundra, desert and mountain passes at 80 miles a day, a velocity unmatched until the invention of the tank. Historians call them brutal nomads living off the land. But that is a myth. The truth is far more advanced. They engineered a self-sustaining logistical engine that eliminated the need for a supply chain entirely. We're deconstructing the 15 interlocking innovations, from food biochemistry to mobile infrastructure, that sustained an unstoppable empire. The first three solved the problem of food preservation centuries before the invention of the refrigerator. The cornerstone of the Mongol food matrix was Borts, the invention of absolute protein density through cold climate freeze-drying. The process began in late autumn, when temperatures plummeted below freezing. Mongol food preservation specialists sliced lean beef, yak or horse meat into long, precise strips and hung them under the ventilated eaves of their shelters. They did not cure the meat with salt, nor did they dry it with heat. Instead, they let the dry, sub-zero Arctic winds go to work. Over a period of months, the freezing air triggered a natural process called sublimation. Moisture inside the meat's cellular structure transformed directly from solid ice into water vapor, bypassing the liquid phase entirely. This prevented the formation of large ice crystals that would tear cell walls and ruin the texture, while completely halting the biological processes that allow bacteria to multiply. Once the moisture content dropped below 10%, the meat was ground into a fine, highly concentrated powder. An entire cow's worth of high-quality protein could now be packed into a single, lightweight horse bladder bag worn on a soldier's belt. To prepare a nutrient-dense hot meal capable of sustaining a frontline scout for 24 hours, the soldier simply added a single handful of Borts powder to a pot of boiling water. It was the world's first industrial-scale, lightweight MRE. To solve the issue of carrying dairy rations across vast distances without spoilage, the Mongols developed the first systematic method for mass-producing sun-dried powdered milk. Mongol camp workers boiled fresh mare's or cow's milk in massive iron cauldrons, continuously skimming off the heavy cream paste. The remaining skimmed liquid was then spread onto wide, flat wooden surfaces and left to dry under intense solar radiation until it formed a solid, unspoilable, crystalline crust. This crust was ground down into a shelf-stable powder. Every morning before a long march, a soldier would pour roughly half a pound of this milk powder into a heavy leather flask attached to his saddle, filling the rest with water. As the horse trotted across the terrain, the continuous high-velocity kinetic agitation naturally churned, pasteurized, and paste reconstituted the liquid. By midday, the internal friction transformed the raw powder and water into a perfectly blended, calorie-dense creamy porridge on the move. The soldier could feed himself at a full gallop without stopping the advance for a single minute. While many nomadic cultures drank fermented milk, the Mongols standardized and scaled its production into an exact biochemical preservation system. They used it to brew erag, also known as kumis, a highly stable, mildly alcoholic beverage made from fermented mare's milk. The secret lay in the Khukhuur, a large bag engineered from thick, smoke-cured horsehide. The interior walls of the Khukhuur were intentionally primed with an active starter culture of wild yeasts and lactic acid bacteria. Fresh mare's milk, which has an exceptionally high lactose content compared to cow's milk, was poured inside. The mixture was then subjected to a strict operational protocol. It had to be vigorously beaten with a heavy wooden plunger, or buller, thousands of times a day. This continuous mechanical churning forced oxygen into the liquid, driving rapid aerobic fermentation. Lactic acid bacteria converted the lactose into lactic acid, dropping the pH level below 4. creating an environment so acidic that harmful pathogens could not survive. Simultaneously, the yeast converted sugars into carbon dioxide and ethanol. The result was an unspoilable, vitamin-rich liquid that remained perfectly stable across tropical jungle humidity and Siberian blizzards. The Mongols avoided the scurvy outbreaks that crippled later sedentary European armies by maintaining a radical, high-density nutritional cycle. Their diet relied on a continuous intake of fresh animal blood and nutrient-dense organ meats. The liver and spleen are exceptionally rich in vitamin C, combined with the active probiotic and vitamin-rich profiles of fermented mare's milk known as Aaruul. This combination provided a complete bioavailable supply of ascorbic acid that kept the army functioning without a need for vegetable cultivation or citrus. To preserve the remaining milk solids during peak summer production, the Mongols engineered Aaruul, a rock-hard, dehydrated curd cheese designed to last indefinitely across any climate barrier. The byproduct of the airag-making process was boiled down until it thickened into a dense, chalky curd paste. This paste was sliced into thin, uniform strips or pressed into geometric cakes and arranged on wide, slatted woven mats, placed directly on top of their dome-shaped shelters to bake under the unobstructed steppe sun. The intense solar radiation and constant breeze pulled every remaining molecule of moisture out of the curd, steadily densifying the matrix until its moisture content reached zero. The resulting cheese blocks were so hard they required a knife to slice, making them completely impervious to insect infestation, mold growth, or rot. Soldiers kept pockets full of Aaruul to chew on during multi-day scouting missions. As the hard cheese slowly dissolved in the mouth, it provided a steady stream of highly bioavailable calcium, fat, and protein, fueling the rider's muscular endurance across weeks of continuous tracking. An army can only move as fast as its shelter, and the Mongols completely out-engineered the rigid, heavy canvas tents of Western and Asian militaries by inventing the modular aerodynamic Ger, commonly known as the yurt. The structural foundation of the Ger was a collapsible accordion lattice frame made of flexible steppe wood, held entirely in place by a single, tightly woven structural tension band. It used no nails, heavy metal bolts, or rigid structural joints. The entire framing system was engineered to distribute structural load evenly across a flexible tension matrix. Covering this wooden skeleton were thick layers of compressed sheep's wool felt, treated with animal fats to make them entirely waterproof. Because the GR is completely circular with a low-profile dome profile, gale force winds of up to 80 miles per hour seamlessly glided around the structure rather than catching flat surfaces. This distributed wind load minimized stress on the frame. The thermal properties of the compressed felt created a highly efficient barrier. It trapped heat inside during sub-zero winters, yet remained highly breathable in desert heat. Most importantly, a three-man team could fully assemble or pack away a massive 30-foot Ger onto the backs of a few pack animals in under 30 minutes. It was a high-performance modular tactical barracks that cost nothing in heavy timber or metal hardware. To transport their elite heavy weapons, treasuries and processing equipment across trackless terrain, the Mongols did not rely on standard narrow carts that easily tipped over in ruts or mud. They invented the Kuren, massive, wide-axle mobile city platforms. These enormous wooden wagons featured deep-set axles spanning up to 25 feet wide, fitted with massive solid wooden wheels taller than a grown man. These gargantuan platforms were pulled by coordinated teams of up to 22 oxen working in a synchronized drafting matrix. Because the wide axle distributed the immense downward weight over a massive surface area, the wagons could roll cleanly across soft marshy tundra or deep desert sand, where standard medieval supply wagons instantly bogged down and broke their axles. These floating platforms allowed weapon fabrication workshops, leather curing stations, and mobile command centers to travel continuously across the steppes, keeping the army fully supplied without ever pausing production. Hydration in highly contaminated or alkaline desert waterholes was a constant threat to invading forces. The Mongols countered this by engineering a specialized, seamless rawhide hydration canteen. Instead of stitching pieces of leather together, which creates seams that easily dry out, crack, and harbor toxic bacterial growth, the Mongols harvested intact tubular sections of animal hide from the limbs or necks of livestock. The rawhide was turned inside out, thoroughly scraped, and subjected to an intense curing process using boiling water and animal fats, transforming the flexible protein fibers into a tough, waterproof skin. Inside the neck of this seamless bladder, they packed multi-layered filtration inserts consisting of tightly woven horsehair fabric and crushed willow charcoal. As the canteen bounced against the side of the saddle during long rides, the natural kinetic agitation forced the water back and forth through the internal carbon matrix. This continuous filtration stripped out fine particulates, neutralized bitter alkaline tastes, and reduced waterborne pathogens, providing the rider with clean, soft water in the middle of hostile terrain. An army on a multi-year campaign across distinct climates will rapidly deplete its iron supply through broken arrowheads, chipped sabres, and damaged horse tack. The Mongols solved this metallurgical bottleneck by inventing portable earth core pit furnaces. Instead of building heavy, permanent brickstone masonry kilns, Mongol engineers dug deep, teardrop-shaped combustion pits directly into the natural clay-heavy soil of the steppe. The natural earth walls served as thick insulation, trapping massive amounts of thermal energy far better than a hasty stone structure. To drive the furnace to the high thermal thresholds required to melt iron, above 2,000 degrees Fahrenheit, they connected the pits to large, multi-chambered rawhide bellows. These bellows were driven by a mechanical rotary wooden frame hooked directly to a circling horse. By utilizing horsepower instead of human labor to pump the bellows, they generated a continuous, high-volume oxygen blast into the charcoal-fueled pit. This allowed mobile vanguard units to smelt iron, cast hundreds of thousands of specialized arrowheads, and repair heavy armor in the field without relying on a distant industrial center. The ultimate weapon of the Mongol army was an advanced piece of materials science, the asymmetrical Quad-Composite Recurve bow. They didn't invent the bow, but they perfected a multi-layer lamination technique that pushed its performance past modern engineering standards. The bow was constructed by fusing 4 distinct materials: a flexible water buffalo horn belly to handle extreme compression, a rigid bamboo or birch wooden core to provide structural shape, a highly elastic animal sinew back to handle extreme tension, and a protective outer layer of birch bark to seal out moisture. These layers were bound together using a specialized glue cooked down from fish bladders, which took up to a year to cure at the molecular level. This composite created an incredibly powerful mechanical spring. It possessed a staggering draw weight of up to 160 pounds, storing more kinetic energy per ounce of material than modern synthetic carbon fiber. Critically, the design was engineered asymmetrically. The lower limb was slightly shorter than the upper limb. This precise geometrical adjustment allowed the rider to cleanly pivot and fire the weapon across the neck of a galloping horse without the lower bow tip striking the saddle or the horse's flank. It was a high-output artillery piece optimized for a fast-moving cavalry platform. Coordinating tactical movements across miles of terrain under the screaming chaos of a battlefield is impossible with vocal commands or standard flags. The Mongols bypassed this limitation by inventing the whistling signal arrow. Mongol craftsmen carved hollow, bulbous tips out of animal bone or horn and drilled precision-angled aerodynamic slots into the sides. These hollow heads were mounted onto the tips of lightweight willow shafts. When launched from a high-powered composite bow, air rushed through the precision slots at extreme velocity, generating a piercing, high-frequency acoustic shriek that cut through the thunder of thousands of galloping hooves. By varying the angle and size of the slots, they engineered different acoustic pitches. Commanders could launch specific whistling arrows to transmit precise tactical commands, such as a sudden retreat, a flanking maneuver, or a concentrated volley, across miles of open terrain instantly. completely outmaneuvering traditional messenger-based communications. Heavy European iron chainmail or solid plate armour was completely unsuited for the rapid long-distance movements of the Mongol cavalry. It was heavy, restricted lung expansion and rusted rapidly in humid river basins. The Mongols engineered a high-performance alternative, oil-cured rawhide scale armour. They took thin, flexible scales of raw cattle hide and soaked them in a boiling solution of water, natural lacquers and animal tallow. This chemical treatment permanently altered the hide's molecular structure, cross-linking the collagen fibres and turning the soft skin into a rigid, impact-resistant shield. These rawhide scales were then laced together using silk cords in an overlapping pattern, creating a flexible armour vest that weighed a fraction of Western iron armour. Because the scales overlapped like fish skin, they distributed the blunt force impact of a club or mace across a wide area, while the hard, lacquered surface easily deflected steel arrowheads. Furthermore, the oil treatment made the armour completely waterproof, preventing it from softening or rotting when transitioning from arid deserts to humid tropical wetlands. Logistical efficiency is driven entirely by organisational design. To eliminate the chaotic, unpredictable family clusters that plagued traditional tribal militaries, Genghis Khan invented the Arban system, the total algorithmic standardization of an organization's social architecture. He completely dissolved ancient tribal and bloodlines, reorganizing every male over the age of 14 into a strict decimal command structure. 10 men formed an Arban, 10 Arbans formed a Jagun of 100, 10 Jaguns formed a Mingan of 1,000, and 10 Mingans formed a Tumen of 10,000. This was not a loose grouping. It was a legal and physical binding matrix. If a single man from an Arban deserted or showed cowardice in battle, the remaining 9 men of his unit were instantly executed. If an entire Arban fled, the entire Jagun was executed. This brutal algorithmic accountability created an unbreakable pack bond. It completely eliminated the need for an internal military police force, ensuring total operational compliance and flawless execution of complex tactical maneuvers across thousands of miles. To maintain absolute control over a sprawling empire and prevent internal military coups while the frontline armies were thousands of miles away, the Mongols invented the Keshik, a highly sophisticated political defense matrix. The Keshik was an elite palace guard consisting of 10,000 soldiers recruited exclusively from the sons and younger brothers of conquered commanders, tribal chieftains, and high-ranking generals. This recruitment strategy was brilliant. It gave the sons elite status and top-tier military training, while simultaneously transforming them into high-value, active hostages residing directly within the emperor's palace. The Keshik operated on a strict, rolling day and night rotational shift. The night guard held supreme authority. Even a high-ranking general could not enter the palace grounds during the night shift without their explicit permission. By keeping the families of their distant military leaders bound directly to the daily security operations of the capital, the Mongols created an internal political anchor. It guaranteed absolute loyalty and secure supply chains across the entire empire, ensuring that a general fighting in Europe would never turn his army back toward Mongolia to attempt a coup. The absolute peak of Mongol infrastructural engineering was the Örtöö, the world's first transcontinental, modular postal and logistics highway network. Rather than relying on individual couriers attempting to ride a single horse across an entire continent, the Mongols engineered a standardized continental relay grid. They built permanent manned stations spaced precisely 25 to 30 miles apart, the exact distance a high-end steppe horse can travel at a full gallop before hitting complete physical exhaustion. Each station maintained a constant pool of up to 20 fresh, well-fed horses, deep food reserves, and an active security garrison. When an official courier arrived at a station bearing a vital message or critical tactical data, he didn't rest. He instantly leaped onto a fresh, rested horse and galloped toward the next node. If the courier was physically exhausted, he passed the message packet to a rested station rider who took off immediately. This modular relay system allowed information and high-value supplies to cross up to 200 miles in a single day. It effectively condensed the vast geography of Asia, allowing the Central Command in Mongolia to receive intelligence reports from European borders faster than a modern medieval kingdom could send a message to its neighbouring province. To secure the immense movement of information and wealth across the Örtöö network, the Mongols invented the paisa, the world's first uniform, multi-tiered diplomatic passport and encryption device. The paisa was a physical tablet crafted from gold, silver, iron or wood, worn explicitly on the courier's belt or horse harness. It featured deep official inscriptions declaring the absolute authority of the eternal sky and the emperor. The level of metal indicated the courier's rank and clearance level within the imperial logistics network. The paisa acted as a physical key to the entire continent's infrastructure. When a courier entered any village, city or Örtöö station and flashed the tablet, the local population was legally required under pain of immediate death to surrender their finest horses, fresh food and secure lodgings to the bearer. It acted as an ironclad insurance policy for international merchants and diplomats, completely eliminating the local tolls, bribes and security risks that had paralysed global trade for centuries. The paisa transformed the dangerous fragmented Silk Road into a secure, unified free trade corridor running under a single legal authority. The Mongol framework operated on the opposite principle of today's economy: maximum results derived from zero mechanical input. They didn't build a massive commercial grid. They engineered self-sustaining systems that ran on physics, not maintenance contracts. We didn't lose this technology because it failed. We set it aside because resilience isn't profitable. But in a world where a single-stranded ship can freeze billions in trade, the fragility of our efficiency is becoming our biggest liability. If you're done accepting broken supply chains as the price of progress, subscribe to Silk Road Diaries. I want to hear from you. Which of these 15 innovations would you trust to keep your own world running when the grid fails? Let me know in the comments, and I'll see you in the next one.